Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay. Let me start. Okay, so we will continue from where we left last Thursday, right? So what we'll do today is we'll go over the system of equations. We already saw this some time back, but then what we'll do today is we'll go in a sequence. So we'll first understand what a system of linear equations is, right? So then we look at Ax equal to 0. That's the homogeneous system. So homogeneous. Okay. And then we look at the general Ax equal to B form. Then we look at what happens if you can't solve Ax equal to B, right? So that is what we'll look at next. So this is closely tied to this concept called linear regression. Okay, so you might have briefly looked at linear regression in week 1, right? When Professor Harish was explaining supervised and unsupervised learning, he might have touched upon linear regression as one of the classical supervised learning problems. So that is very, very closely connected to this approximation Ax approximately equals to B, right? So we will look at the connection and then we will solve this linear regression problem using what is called least square. So these three are actually linked. 4, 5, 6 are linked. 4, 5, 6, 7 are linked. So, and then we look at, finally, we'll close with what are called projections and projection matrices. Okay, so that is the sequence in which we go. Okay, so if you have any questions, you can stop me and we can discuss. Okay, right now you already know what a system of linear equations, what a system is, right? So there are m equations in n unknowns, right? So this is the standard form, and you have say a11 x1 plus a12 x2 so on till a1m x, so a1n, right? So there are n coefficients, so in each row that is equal to b1, right? And then you have likewise you'll have a21 x1 so on and so forth all the way up to a m1 x1 plus a mn xn equal to b n m, right? So this is a system of m equations, m linear equations in n unknowns, right? So this is what we call a system of equation. Now, if you collect the coefficients in a matrix, okay, and the right hand side in a vector, the right hand side and the unknowns, right? In vectors, right? So if you do that, you can transform this into a matrix vector product on the left hand side equal to some other vector. Okay, so what is this? You have to always keep track of the dimensions. So A is of shape m cross n, and x is a vector in Rn, right? So and B is a vector in Rm. So this is clear, right? So this is the basic idea. Now, the way to understand, so this is correct. This is a proper way of understanding it. But then there are other ways of looking at it. So I'll mention two ways of rewriting the same equation so that we are able to understand the solutions better, right? Or how to solve them better. So first is we look at Ax itself, right? So what I'll do is instead of looking at A as m into n entries, so it's a matrix. So this has m rows, n columns. So there are m into n entries, and we have laid it out like this in the form of rows, right? So here the focus is on the row form of Ax equal to B, right? So each row we are separating it out. That is perfectly fine. In fact, we will stick to that, and I'll show you how you can rewrite it. So if you call each row A, some A1 transpose, right? So this is first row. So A1 will be what? The n components here, right? So that will be A1 transpose. I'm using transpose because it's a row vector. So the first row, I'm going to call it A1 transpose. So likewise, if I go down, I'll have m rows. So there are m row vectors. Each row vector is in what space? Rn or Rm? N or M? N, right? So each one is an Rn. So that this is like the row picture. Hilbert Strang calls it the row picture, I think. So you can treat each row of A as a row vector. Okay, so the ith row, for example, that's theta. I have theta from that. So the ith row is called AI. Okay, so I'm going to call it AI and AI transpose, and it is in Rn. So therefore, what you can do is you can actually denote AX equal to B as these M equations. Okay, so A1, so this is, notice what operation is this? If A1 transpose is a vector, row vector, X is another vector, like what exactly are we doing here? Exactly, right? You're doing a dot product. So this is the dot product of A1 and X, right? So this is A1 transpose X equal to B1. So that's what this is actually. The first equation is nothing but A1 transpose X equal to B1. And second equation is A2 transpose X equal to B2, so on till AM transpose X equal to BM. Okay, so this is one way of looking at the same system of equations using row vectors in terms of dot products, right? So left hand side is a bunch of dot products and right hand side is some component of a vector. So this is one way of looking at it, and I want you to keep this in mind. We'll come back to this later. So there is another way, which is the column picture, which is even more interesting because that will help us understand so many things related to solving equations. So that is as follows, right? So instead of looking at this as rows, you are going to look at this as columns. Now each column consists of a set of A values, right? So I'm going to call that A. So you must not get confused between this A that I am using here and the other A. So here I'm calling each column as A1, A2, so on. Okay, so this is AN. Now there are n columns, remember. Okay, so these are n columns. Okay, don't confuse yourself with this. So this is called an abuse of notation when you use the same thing for two different ideas. So here A1 is different from this A1. Okay, so I can use another variable, but this should be clear from context. All right. So what we are doing here is, if you represent each column as A, what are you doing here? You are multiplying the first column by x1, second column by x2, and then the nth column by xn. So you can rewrite the left hand side as A1 or x1 into A1 plus x2 into A2 plus xn into an equal to b. Okay, so when A is expressed as a collection of n column vectors, then Ax is the linear combination of the columns of A, right? So this is therefore the LHS is a linear combination of vectors, of you call vectors or you call it columns, right? What are you asking? So if you want Ax equal to b to have a solution, if Ax equal to b should have solution, or if it is to be consistent, it is another term that you use, right? So if it is to be consistent, consistent means it has a solution. Then B should be in the
column space of
A, right? So that is the main catch. So what is the column space of A? Recall that it is the set of all linear combinations of columns of it, right? Span of A. So alternatively, we can express this as B. So I just box this because it's important. A system of equations Ax equal to B, linear equations, is consistent if and only if, right? If and only if means both directions should hold, right? If and only if B is in span of, or I could just say C of A, right? Whereby C of A, where C of A is the
column space.
column space of A. Okay. So is this clear? This is the first step that you need to know.
Yes, sir.
Okay. So this is the general idea. Now there is a picture that we can draw. So this is a picture that I'm very fond of, which actually I took from another set of notes, which you can keep on refining. So we will come back to this picture once in a while, every time we make some progress. So that is as follows. So you have, if you want to see if Ax equal to B is solvable if it is consistent, first question is you ask if B is in the column space of A. Okay. So that's the question. So this is a question. So the question has an answer, right? So it has a binary. It's a binary question in some sense. So it's a question mark if you have. Is B in column space of A, right? So there are two branches that are possible. So there is one branch which says yes. Okay. So that is yes. That will go here. And then there is another branch that will say no. So that will go here. And so if it says no, currently what can we conclude?
System is inconsistent.
Consistent, right? So this is the conclusion. We'll come back and see that even if it is inconsistent, we can find an approximate solution. That's what we'll come to. That's the whole least squares linear regression link that we'll explore. But if there is a solution, then there are actually two possibilities. What are the two possibilities?
Unique or infinitely many?
Yeah, so there are the nature of the solutions, right? So there could be a unique solution and there could be infinitely many, right? So we will come to this. So this is what we look at once we finish Ax equal to 0 and the general solution. We will know what question should we ask. So we'll ask one particular question is dash 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 whatever, right? So depending on the answer, it will lead us to either infinitely many or unique solution. Okay, so can we move on to the next section?
Yes.
Okay, right. So we start with the most fundamental system. We have already seen this, right? How do you solve this? The algorithm we won't discuss today because you know this. So you have to do the Gaussian elimination row reduced form, row echelon form, and then you will find out what are the pivots. So maybe quickly the algorithm, right? So this is not the focus of today's session. So, but anyway, so find the.
Today we are covering which week, sir?
We are covering week 3.
Okay, and this is within which section of it? Like
It is, yeah. So this is kind of not exactly what Prof has covered. I am kind of giving you. So the aim of the session is to give you some background material so that you can maybe understand the lectures better.
Okay.
Okay, so that's the aim. So find the RREF of A, right? You will find the RREF of A. Identify pivots and pivot columns. Identify three variables and what is the other thing called?
Dependent.
Dependent or pivot variables, right? So you find out free and pivot variables, and then you set exactly one of the pivot variables to one, or rather you from here I'll just say follow the usual procedure, right? So you set one of the pivot variables, free variables to be 1, rest to be 0, and you solve for the pivot variables. So you do all that. Okay, we saw one example last session, so I'm not going to repeat that. Instead, what I'll do is I'll focus on slightly different things. Now, the set of all solutions to Ax equal to 0 is called the, what is this called? There is a name for this.
Homogeneous.
Nullity.
Nullity is the dimension of something, but what is that?
Null space, I think.
The null space.
Null
Right?
space.
So it's called the null space of
space.
A, and denoted by this we saw this, right? So there's the one of the four fundamental subspaces. So it's denoted by n of A. Now this will, from this you can actually conclude the following: if AX equal to 0 has a unique solution, then null space of A is equal to what?
0.
Yeah, it's the 0 subspace, right? So it's the subspace. So remember, first thing is that we already saw this. Null space of A is a subspace. I'm repeating this, but it's okay to repeat such things. So subspace of its space of Rn, right? So null space of A is a subspace of Rn, and if Ax equal to 0 has a unique solution, then null space of A is 0. Okay, I hope you are all able to see this.
Yes, sir.
Okay, when will null space? So when will this happen? How? So what is the relationship between this and the columns of A? So if columns of A are of certain character, then the null space of A will just have 0.
If the column space spans the entire space.
Correct. Can you put it slightly differently? So that is correct. So if the column space spans Rn, so if the column space spans Rn, then what do you conclude about the columns?
It is equal to the rank range of A.
Correct. That is, yeah, you're right. Okay, so
Independent columns.
yeah, independent columns, right? So both are correct. So if the columns, so when does this happen? This happens when, okay, I put it, yeah, both are right. So if the columns are
Linearly independent.
okay, so you have n columns and they are all linearly independent. So, or this is also correct. So if the columns span Rn, okay, which means that the columns form a spanning set for Rn. Or if you combine the two, then what can you say? If the columns form a
Basis.
basis
Basis.
for Rn. Okay, so all of them are correct. So you should also be able to connect this to the whole algorithm that we discussed before, right? So this will happen if there are no dash variables.
Dependent variables.
If there are no free variables or
Dependent variables.
independent. So I mean, yeah, no independent variables, right? So if there are independent variables, then you can arbitrarily set them. You can generate infinitely many solutions. So if there are no free variables / independent variables, then this will happen, right? So there are like a half a dozen ways of looking at the same thing, and you must be familiar with all of them. You must be able to go back and forth. You can also write this as if there are these many pivot variables.
N pivot in case of n cross n matrix.
Yeah, if there are n pivot variables. Okay, so you can also say that if dash is dash, so there is some property of the matrix which will allow this to happen.
Rank is equal to number of columns n.
Yeah, if the matrix A
Full
is
rank.
has full column rank, right? Has full column rank. Okay, if the matrix particularly is square, so n cross n, what can you say in addition to all of this?
Determinant is non-zero.
Yeah, so if in addition the matrix A is square,
Non-singular.
the above, so this is also, then this will happen when determinant is
Matrix is invertible.
non-zero, or it can also be called, or when A is invertible. So there are many things, but there is a warning, right? So there is a warning. This is an important thing. Usually, you have this tendency to directly think about things as square matrices, right? Whenever you look at Ax equal to B, the immediate tendency is to say A inverse B, okay, or A inverse 0. Okay, so please avoid that tendency. the matrix is very rarely a square matrix. Okay, it's most of the times rectangular. So these are the ways you have to understand, and only in a very special situation will you actually have a square matrix. Okay, so you have to keep this in mind. This should be the last way to understand homogeneous systems. Okay, this is not wrong, but it's a very special case. All right, so that is Ax equal to 0. Let's know that is enough. We have spent enough time here. Okay, so now we look at Ax equal to b, and maybe very quickly.
Hello.
Yeah.
So if ax is equals to b has a unique solution, and and a is invertible also, so will it mean that the matrix A is square and symmetrical both?
Symmetric doesn't come here, right? So only the fact that A is invertible counts. It may not be symmetric. Symmetry has nothing to do with the existence of solutions, right?
Acha, okay.
So yeah.
But
Okay, so this Ax equal to b, do you all want to look at it in terms of an example, or is this theory business itself fine? Which one is better? Depending on what you say.
Example we can better relate to. Say.
Sorry?
Example is where we can better relate to.
Okay, so we'll maybe do a very quick example. Okay, so Ax equal to b. We'll do the whole thing maybe for this. 1 minus 1. Okay, I don't want minus. Minus is like confusing, so I'll just say this is 0, 1, 2. 0, 1. Okay, this is some x. X is x1, x2, x3, x4 equal to let's say, I'm making it up, right? So I could as well make it something nice, something which I can. So I want 1 times the first column. Maybe here a minus, here also no minus sign. Okay, 1 times the first column. So I'll add 1 to 1 plus 2 times the second column. So that is 0 plus 2 plus 4. Okay. Plus 0 times the third column. Let's say third column doesn't contribute. Plus 1 times the fourth column. So that would be 0 plus 1 plus 1. Okay, so this is what this gives me what vector 1 plus 2, 4, 5, 4, 5, 6. Okay, just want to make sure it's correct. 1 to 1, 0 to 4, and 0, 1, 1. So that's 1, 5, 6. Okay, just remember this. One of the solutions has to be, check later, right? So one of the solutions has to be 1, 2, 0, 1. Okay. Yeah. So this is a consistent system. We all agree what we have here, because it is solvable. So now because you should not worry about this part. That is just so that we have something to work with. Yeah. So how do we proceed now? Step 1 is what?
We make equation.
Row reduce it.
Yeah, but even before row reduction, what do we do first?
Augmented matrix.
Augmented matrix.
Augmented, yes.
Yeah, so we first form the augmented matrix. So copy this, and okay, so this is 1, 5, 6. Then we start row reduction. So we'll go all the way till the row reduce row echelon form very quickly. Okay, so this is where we start, and what can we do first?
R2 minus 2R1.
R2 minus 2R1. R2 is R2 minus 2R1. So this gives me 0. What happens to this?
Same.
Same. Okay. What happens to this?
-3.
-3. Yeah. Correct.
Yes, sir.
Okay. What about 5 becomes
3.
3. Okay. All right. So what next? What could I do?
R3 minus R1.
Okay, R3 is R3 minus R1. So this becomes 0. What does this become? 2. 1 minus 2. So -1. 1 remains the same. 6 minus 1, 5. So if I'm making a mistake at some point, you should please correct me. Otherwise, I'll keep going on. Okay, right. So what next?
R3 minus 2 times of R2.
R3 is R3 minus 2 times R2. Okay. So this is 0. This is -1
Plus
plus,
6.
right? So what is that?
Plus 5.
5. This is 1 minus 2, correct? -1. This is 5 minus 6, which is -1. Is this correct so far?
It looks.
Okay, so if it is wrong, let me know. What should this be? What can I do now?
Make this 5 as 0, like 3 times of R3 minus 5 times of R2. Oh, sorry, plus.
1 by 5. Right?
Yeah, I can do 1 by 5, right? Yeah, so 1 by 5. So R3 is R3 by 5. We'll make it 1 and there's a different fraction which is like slightly better. Okay, this one. So this is -1 by 5 and
1.
-1 by 5
1 by
again.
5.
Correct. So is this correct
Yes.
so far? Okay, let's do RREF. I want RREF. Okay, so you could stop at REF also, but it's kind of, it's just, let's go the distance. So what should I do to make it RREF? R2 should become
R2 plus 3R3.
yeah, R2 plus 3R3. Okay, but there will be this all 1 by 5 business coming in. Should we do it or should we leave it like this? Yeah, I think there are too many fractions, so I am not fond of fractions. Okay, maybe we'll leave it like this. We can figure it out later. So we'll stop here. So what are the pivots? This is a pivot. This is a pivot. Now step 4 is what? Step 3 is identify the pivots and the pivot columns. Okay, so these are pivots. We have 3 pivots. And can you have more pivots for this case? Is it possible to have more than 3 pivots here?
No, sir.
No.
Oh, right. So here, this is the maximum.
Yes.
Okay. So pivot columns are therefore the first 3 columns. So sometimes it's convenient to have the variable. So this variable is not a part of the matrix. It's just that it's good to keep track of what is what. Okay. So that is done. So step 4 is identify free and pivot variables. So the free variables here are, okay, first pivot variables are
X1, X2, X3.
x1, x2, x3, and there is exactly one free variable. Okay, so x4 is a free variable. Now we can solve, right? So step 5 is to see the goal is to the goal is to find the set of all solutions to Ax equal to b, assuming that it is consistent. Okay, not consistent, we'll come back to that later, but the goal is to find the set of all solutions, which means if there are infinitely many solutions, you must find a way to represent them. Okay, so that's the goal we are moving towards. So how many solutions are there here? Finite or infinite here?
Finite, I think.
Okay, what about x4? Can't x4 take any value? So
Can take
identify.
any.
Yes.
Okay, I'll maybe add this as a step. So since there is a free variable, the system has
Infinite
Infinite,
solutions.
infinite
infinitely many solutions, right? So that's not really a step, but it's okay. So therefore, you can, moment you have infinitely many, you can find what is called a particular solution, okay, and a general solution. So I am going to look at what is called a particular solution is some solution to the system. And the way you can do this is, there are many ways to do it. The easiest way, find one solution, right? I'm going to call that find one solution, is to set the free variables to 0. Okay, this is a common step. So if you set the free variable to 0, then you can solve for pivot variables. Okay, so this is one way to find one solution, which you are going to call the particular solution. So in this case, I'll list down x1, x2, x3, x4. Okay, x4 I'm going to set it to 0 because it's a free variable, and then I am going to solve for x1, x2, x3, x1, x2, x3. Okay, so I'm starting. So these are not zeros. So we'll start with x3. This is backward substitution. So set the free and solve for the pivot variables using
Backward substitution.
right? So this is important, right? This is called backward substitution because you are going from back. You are going back. So this row reduction, also called forward elimination, right? So because you are going forward and eliminating one row at a time, you are going down. Okay, this is going back. So what is x3 from this? From all this,
minus 1 by 5.
x3 is minus.
Plus. Okay,
Yeah,
okay.
correct, right? Minus 1 by 5 is correct. Yeah, x2. What is x2? So all this fraction business I hate, but anyway, 3. So it is what 3 is there on the right hand side, and then plus 3x3 will happen, right? So plus 3x3. So this will be what in terms of fractions? So minus 9 by 5. Is that correct? Is that correct? 5. 10 minus 9 is 6 by 5. Let me know if this is wrong. See, I'll break this down into 2 steps. So this is what x2 minus 3x3, x4 is anyway 0. So x2 minus 3x3 is 3, right? So x2 is 3 plus 3x3. Okay, this is the same as 3 plus 3 into minus 1 by 5. So that's 3 minus 3 by 3 minus 3 by 5, is it? Which is what we had earlier, right? 16 minus 3. Is that correct?
12 by 5.
15. Oh, sorry. This is 15 minus 3, right? Sorry, 12 by 5. This is 12 by 5. Now, this is what? X1 is equal to, so x1 plus 2x3. So that is 1 minus 2x3. This will be 1 minus 2 times
24 by 5.
24 by 5. And you end up with
19 by 5.
19 by 5, is it?
1 plus 2 by 5.
Where?
X1
X1 is 1
plus 2 by 5.
Oh, x3 is negative, is it? Okay, yeah. Sorry. 1 plus. Why did I write 12 by 5? Oh, I was using x2. Sorry. Yeah. So 1 plus 2 by 5. Correct. This is what? 1 plus 2 by 5 is 1 by 5, right? So we'll get rid of all the 5's in the denominator. Therefore, a solution to x equal to b is, so 7 by 5, comma 12 by 5 comma minus 1 by 5 comma 0, right? So this is the same as, or not the same as, but let's make it slightly more convenient. So this is 7 12 minus 1 0, correct?
Yes, sir.
Okay, so there is one tool. This is I'm not saying you should always use it, but for those who are anyway going to do machine learning at some point, right? We are going to code, so you must know you can use this tool just to make sure that you are on the right track. Okay, this is just those who are aware of it. This is called NumPy. Okay, so this is this is a collab, and the tool that we are going to use is called library is NumPy. So this is a quick check for us to make sure that we are on the right track. So the equation we are trying to solve is I'm first writing down the matrix. Okay, so the matrix is this is the matrix. So, okay, I'm going to represent the matrix first. 1020. Okay, 1020 is the first row of the matrix, and then you have 2111. So it's 2111, and then you have 1211. Okay, so if you actually run this, you will see that this is the matrix. Okay, it's called an array, but that's not important now. And the right hand side is a vector, right? So the vector is in this case 156. Okay, so that's the vector. So what we have to see is we have computed x to be what did we compute x to be? 712 minus 10. Okay, 712 minus 10. So I have to multiply. So this is x. Okay, now if I multiply a and x, this is how you multiply matrix and a vector in this in Python in this library using this library. Okay, so a into x, this is what I get. See, I made a mistake. You can't divide, you can't just randomly multiply by 5, right? That is only true if you have a homogeneous system. So this has to be 5. You have to keep this in place. So 156, right? So that is 156. Do you all of you find out the mistake that I made? Was it clear to everyone? So see, this is a solution, right? I multiplied this by 5, which you can't do, right? So if you multiply left hand side by, if you multiply x by 5, b will also have to be scaled by 5, right? So this is the solution. You can't do this multiplication business. You can do that only if you are doing ax equal to 0. So this is the solution. Okay, is that clear to everyone what just happened?
Yes, sir.
Okay, so we just verified that this is indeed correct. So 156, what was the right hand side? 156. So this is one such solution. Now this is called a particular solution to the system. Okay, now is this the only solution? It's not, because we have just shown that there is a free variable, so there are infinitely many. So the natural question to ask is, what is the general solution? So by general solution, you mean you should cover all possible solutions to the system. So how do you find that?
We can take x4 as k.
Yeah, x4 as k, and then
Write the dependent variables in the form of the free variables.
correct, right? That's good. So you could do that. That's one way of finding out set of all possible solutions. So we could do that. So the idea is to set arbitrary values for the free variables and then solve for the pivot variables, right? So that's correct. Now we look at a slightly different approach, so which gives you a sense of the structure of the system, the solution space, right? Now this is an algorithm, but what is the general solution going to look like? So you have to notice the following. If xn, right, I'm going to call this xn, is some element in the null space of A, right? Then what is AXN? A times xn is equal to
0.
0, right? Now I'm going to call this XP. Okay, so XP is called a particular solution to the system, and you have to note that A times XP equal to B. Okay, that obeys system. So now what can you say about XP plus XN?
Entire space.
See, XP is this vector that we just found out.
Okay.
Okay, and Xn is some vector in the null space. So what can you say about XP plus Xn? Mainly, is that a solution to the system AX equal to B? Yes or no?
Yes, I think.
Okay,
No,
we try. Yeah, okay, why no?
because it has to be in the column space, and XP plus XN is in the null space.
See, B has to be in the column space, but why that? There's no restriction on X, right? X is anyway in Rn. Xn is also in Rn, right? So both of these are in Rn. So remember that this is in R4, right? So X is in R4, but B is in R3. So the what could be in the column space? B should be in the column space. So that's in R3 here. So that is not the right objection, right? So you get that? So it is a solution. Let's see why. What for it something to be a solution, what should happen? You have to first find out what is A into Xn plus XP. This is what? A into Xn plus A into XP. A into Xn is equal to 0.
Zero.
AXP is what?
B.
B.
Okay. Therefore, A into something is equal to B. Therefore, Xn plus XP is a solution to AX equal to B. Okay, do you get this?
Yes.
Okay, therefore, I've only shown one side of the argument, but you can show that, one can show that, and this is important, so I'll box it. The set of all solutions to AX equal to B is given by a particular solution, or so, okay, I'll put it this way. Let AX equal to B be consistent, right? And let XP be a particular solution. Like the case here, right? So this is AX equal to B. So this is AX equal to B. It is consistent, and one such solution was say 1201, or another one that we found out here, which was 7 by 5, 12 by 5. So this is a particular solution. So you have to assume that this is there. Okay, then what you can show is then the set of all solutions to AX equal to B is given by some particular solution plus the null space of A. Okay, what we mean by that is any solution to AX equal to B can be written as a particular solution plus some element from, or some vector from the null space of A. Okay, this is a very important result. So is everyone convinced by this argument? I have not proved it completely, so I have only shown you one direction. So what I've shown you is if you add the some element from the null space to a particular solution, that is also a solution. Okay, you get new solutions in this process. So is this clear to everyone what we have just done?
Yes, sir.
Okay, so what we'll now do is, this again helps us understand the whole idea of unique solutions and infinitely many. So when does AX equal to B? So if AX, again, all this is assuming it's consistent. If AX equal to B is consistent, when does AX equal to B have a unique solution? What can you say from what you have seen so far?
We have n pivots for
Space is 0, basically.
Yeah, if the null space is 0, okay. What else? So how else can you express the same thing?
Free variables do not exist.
So there are no free variables. So basically, you're right.
Particular solution is the general solution.
Yeah, whatever we did here, entire thing will carry over. Okay. So see, for it to have a unique solution, null space has to be 0. For Ax equal to 0, we did the same thing, right? If you remember. Columns are linearly independent. Here also columns are linearly independent. So columns, okay. Yeah, so it's this. It will be the same thing. Okay, so is this fine with everyone? All these conditions that we listed down will carry over. Okay, any?
Yes.
Okay, so I'll not repeat this. Refer to Ax equal to 0 discussion for other ways of representing this. Okay, null space is 0, column rank is n or rank is n, no free variables, or if A is square then A is invertible. Okay, so maybe this is an important remark. So if A is invertible, then there is a unique solution, and that is given as x equal to A inverse B. Okay, this is the last thing that should be on your mind. Okay, you should know all the other things that come before it. So you can now go ahead and complete this picture. What is the question that you have to ask here? If you want to find out if it's a unique solution or infinitely many, what question do you ask?
Are there any free variables?
Correct. But in terms of the spaces, right? So here we use the column space. So if I want to use a space here, subspace,
Is the
what?
column space linearly independent?
Null space.
0
Yeah.
or
So
not.
is the null space? So is n of A equal to, is it the trivial subspace 0? Okay, if the answer is yes, then what can you say?
Consistent solution.
Yeah, it is consistent, but is it infinite or unique?
Unique.
Unique, right? So you goes here, this goes here. So the null space, it turns out, is a very important thing. So out of the 4 fundamental subspaces, the null space plays a very important role. So it helps you determine if your solution is unique, if your columns are linearly independent. You will also see next week the null space makes an appearance when you calculate the eigenvalues of a matrix very soon. So okay, so that's that. So that's Ax equal to B. Now, any questions so far with respect to what we have been discussing so far? Okay, so we'll move to now the meaty portion of week 3, which is this whole projections, least square, linear regression, and so on. Okay, now maybe club these two because they are kind of clubbed. They are kind of closely related. Now, the first thing is
I have a question here. Can we
Yeah.
can we move to that the kind of diagram that you showed before?
Yeah.
Yeah. Is this diagram completed? Like in what cases is this inconsistent?
So this is not complete. Yeah, so it's complete in the sense that if it is consistent, it's complete. Okay.
Okay.
So
But if it's not in the if it's not in the column space, the system is inconsistent.
Yeah, you can never find a solution. You can never find a solution. So that's where we are now. So we are actually discussing this portion. If it is inconsistent, what is the best
Okay.
that we can do? So that's what we are going to look at.
Okay, okay.
Okay, so that's where we are. So we are now, so Ax equal to B is not always consistent, especially in a practical situation, right? So in a practical setting, you will not have a solution. Okay, so in such cases, what do you do? So in such cases, the best thing to do is to resort to an approximation. So what do we mean by this? This is quite common in engineering, right? So if you look at computing root 2, for instance, right? So let's take the case of computing root 2. Okay, what we do is, so root 2 is an irrational number, as you all know. So there is no, you can never represent it as a real number. So sorry, as a rational number. So it's irrational. Therefore, what you can do is, the only thing you can do is, if you want to compute something that involves root 2 in a very practical setting, you'll have to resort to some approximation of root 2 by rationals. So what is the approximation that we are all quite familiar with?
Linear.
Yes, yeah, that is, you could do root x, you could take and approximate it around x equal to 2. So Taylor series, that you could do that. But in terms of numbers, I must.
1.414 something.
Yeah, 1.414, right? So you could, this is a very common thing we do. So, and depending on the number of decimals you have, the approximation is either close to root 2 or far away from root 2, right? So 1.4, it's a bad approximation. 1.414 is very good. 1.41 is slightly worse. 1.4 is even worse than 1.41. So the idea is, I can't represent root 2 exactly, but I can approximate it. And the way I study the distance or the goodness of approximation is to compute the difference, right, between the approximation I have and the true value, right? And the smaller, so I call this the error, and the smaller the error, better the approximation. Okay, this is for real numbers. So if you want to approximate a single scalar value, so this is what approximating. So this is what you do. Okay, now how do you approximate vectors? So notice that Ax, we now have inconsistent system. Therefore, we need to look for approximations, right? So we are now solving this system. This is called Ax approximately B, meaning can I get close to B? So the idea is, can I get close to B, or can I find an X that will get me as close to B as possible? Okay, so what does this mean? So if you're now dealing with vectors, right? So you have to take that into account. You are no longer dealing with scalars. So let's say B is equal to 1, 2, 3. Okay, and for different values of X, I'll take two values of Ax. Okay, so Ax is what you're approximating, right? So in one case, this is say 1.5, 2.5, 3.5. Okay, and this is like Ax x1, or maybe what do we call this? Is like Ax prime, and you have Ax double prime. Okay, and there is another approximation which is 1.1, 2.1, 3.1. Okay, so it should be clear to you that one of these is better than the other. Which one is better than the other?
Second one.
Second one, right? So, and how do you measure this? So for vectors, for vector approximation, okay, or rather for approximating vectors, what process are you going to follow? That's the question. What process do you think would be the right?
Projection.
Projection, right? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process do you think would be the right process? So what process Right. So even before we go to the projection, I just look at these two vectors. So this is a vector. I want to study these two approximations. So this one,
Just to find the difference, and whichever has lesser value, lesser error. Difference is error. Whichever has a lesser error, we can consider.
yeah. So you follow the same. You extend the logic from the one-dimensional case, right? You find the difference. So there's not one difference. There are in fact multiple differences, right? So or rather, as many differences as there are components. So you have one minus. So if you are looking at error for the first vector, it could be 1.5 minus 1 plus 2.5 minus 2 plus 3.5 minus 3. Okay, you could consider this. But then there is a small problem with just using differences. What is the problem?
They might cancel out.
Exactly, right? So they might cancel out. So for example, instead of having 1.5, 2.5, 3.5, if your values were 1.52 and say 2.5, okay, your error will be 1.5 minus 1.
It's 5 o'clock.
Plus 2 minus, or rather 2.5. No, so 2 minus 2 plus 2.5 minus 3. Okay, I hope that's correct. So now notice that 1.5 minus 1 and 2.5 minus 3, they'll cancel each other out. So you'll get an error of 0. Okay, and that is not reflective of the approximation, right? So what is the point we are making? We could use simple differences to find the as a measure, okay, as a measure of the goodness of the approximation. We could use simple differences, okay, but that has a problem, as the differences might cancel each other out. Okay, so therefore simple differences are probably a bad idea. What could we do then?
Just
Square.
Square, right? So you just consider, therefore take the square of the differences. That is better for several reasons, but at least one reason is that it allows you to get rid of this feature where differences cancel each other out. Okay, so I hope this idea is clear. So what we are trying to do is we are trying to find an approximate solution, and the goodness of the approximation is measured by how close you can get to B in this squared sense. Okay, so this is, you call this the sum of squared errors. Okay, so each one is an error. So this often goes by the name sum of squared errors. There is another term called mean squared error. So that's like if you take the average of this 1/3 times E, that will be the mean squared error. So there are different ways of, but it's the same. The idea is the same. Okay, so far is it clear to everyone what has happened?
Yes, sir. I see it like little contradiction in the statement what you have given. Just could you please go up, sir?
Yeah.
Up actually where A equal to approximate. No, yeah, still understood. See, we now have an inconsistent system you mentioned here. Just 2 lines before you mentioned, the system is not always consistent. Can we consider both the statement? Yeah.
Yeah.
It's not always consistent, which means sometimes it will be consistent also. That time also we can go for approximation, or
No.
here
If it is consistent, you always go for the consistent, the solution that is there, right? So
So it means it's not always consistent means we can consider that as it is always inconsistent.
No, it could be inconsistent, it could be consistent. What I'm saying, see, this is just I'm not making a rigid statement here. What all that I'm trying to say is I'm motivating this section, right? Why do we need to study AX approximately equal to B? Because in real life, you might encounter situations, most of the times, you might encounter situations where AX equal to B is not consistent. You could, if you are lucky, you could have a case where AX exactly equal to B and then you can solve it directly. But it need not always be the case, is what I'm saying. Right? I hope that is clear. So they are not contradictory in the sense, see, this part is just to motivate the whole thing, right? Now, once that motivation is done, we are now looking at only inconsistent systems. So in the end, you will realize that whatever solution we arrive at, it will also work for consistent systems. So we'll come to that. That's whatever we call the least square solution will work even if the system is consistent. But for now, we just assume that it's inconsistent. That's cleaner.
Okay, yeah, got it. Thank you.
Okay, so this is called the sum of squared errors. Now, question is, yeah, how do we solve this? So, is this clear to everyone so far? Any other questions regarding this setup? Okay.
No,
Okay, so do you mind if we just take 2 minutes? We break for 2 minutes and then start the next section, the squares.
yes, sir.
Okay, yeah.
Yeah, hello. Hello. Okay.
Okay, so shall we resume discussion?
Yes, sir.
Okay, linear regression, maybe we'll go here. linear regression and least squares. Okay. Yeah, what we'll do now is we'll consider the following problem. So consider following problem. So you have some data with you. So the data is as follows. You have quiz 1 marks, okay, and you have quiz 2 marks in MLF, let's say, of some students, and you also have the end term marks that is separate, okay, end term marks. No, you are as the administrator, maybe Professor Andrew or whoever, right? So they want to understand, or maybe instructors, so they want to understand how are the quiz 1 and quiz 2 marks influencing the end term marks, or can we use, so this is the question, based on historical data of performance of previous term students, right, in MLF. But this is this is the data you have. Based on this historical data, you as an administrator want to understand or want to predict, okay, how students in the current term will perform in the end term based on the Q1, Q2 scores. Okay, is this problem statement clear? So
Yes.
yeah, we have data with this. So for example, you have like thousands of students who have done MLF, but for simplicity, let's say we only have 5 students. We'll take as a representative sample only five students. So they have, let's say, 56, 8 and says 70 quiz 1 and quiz 2, and the student's end term mark is 80. Okay, maybe some other student is there who scored. I'll keep all numbers round figures, right? So 60, 60. And in term also they got 60, let's say. Someone is there who got 70 and 80, and they got 60. And there is someone who got 100, 90, and 90 or 80, whatever, right? So four students, and quiz 1, quiz 2, and enter marks. So this is your historical data, or what is usually called the training data set in machine learning terms, right? And using this, somehow you have to find out, or you have to predict, you have to come up with a model or a machine that can predict the scores of end-term students, right? Even before they write the end-term. So that's when prediction is useful. So there's no point predicting something after it has happened. So after quiz 1 and quiz 2, you predict their end-term scores using their quiz 1, quiz 2 marks. Okay, that's the target. That's the goal. So this is a simple example of a linear regression problem. It's not yet linear. So this is an example of a regression problem, right? So it's regression because you want to predict a real number. Okay, in this case, the real number is marks. So I hope the problem is clear to everyone, right? So this is regression. Now, if the model that you choose to represent the relationship between the labels and the features is linear, then you have linear regression. Okay, so let's quickly look at what are the features here. What would we call the features?
Quiz 1, quiz 2 marks.
Yeah, so the features are Q1, Q2 marks. And what is your label, or what is your target?
End-term marks.
End-term marks, okay. So this is the setup, and okay, so I call the end-term marks E, quiz 1, quiz 2 marks of a student Q1 and Q2. Okay, now remember that this is the true, what we call the real label or true label. So this is the reality, but in general, you don't know what you can only predict. Okay, so therefore we'll call whatever prediction we make E hat. Okay, so if it's a linear model, what can I do? How can I represent E hat in terms of Q1 and Q2?
Q1 multiplied by that matrix plus Q2.
Okay, do you need a matrix here or?
Some Q1 times X or Q2 times.
Yeah, so some X, right? So let's say some X1 Q1 plus
Plus or minus.
plus X2 times Q2 plus, for added benefit, you can call
C.
this X0, right? So some constant, right? So this is an example of a linear regression model. Okay, so this is for one student. Okay, in general, this is how the equation will look like. So based on X1 and X2, you could have, if for each student, you can come up with the predicted score. So how do you represent this now concretely, right? So this is, I'll call this, so this is what 50, 70, right? So 50 X1 plus 70 X2, right? For simplicity, let's leave out the X0, okay? This is the first predicted value. I actually don't know if this is equal to 80, right? So it in all likelihood, it will not be equal to 80. Therefore, only thing I can hope is this is something approximately equal to 80. Okay? Are you all with me so far?
Yes.
Okay. So for the second student, likewise, 60, you have 50, 60. Yeah? So 50, 70, 60, 60. So it's like, just for completeness, I'm going to do the whole thing. So this is approximately what? 60. And the third student is 70, 80. So 70 X1 plus 80 X2 is approximately 60 again. And finally, you have 190. So 100 X1 plus 90 X2, approximately 80. Okay. So this is the practical situation that I was talking about. So in practice, this is what is called an overdetermined system, meaning you have more equations than unknowns, right? So you can, so in this case, it's only 4 students, but in general, imagine there will be like at least 5,000 students who have done MLF so far. So you have 5,000 equations and only 2 unknowns, right? So you can never solve AX equal to B. So this will be a case of A. I'll just copy this because this is directly there with me. So this is a case of, this is typical case of AX approximately equal to B that I was talking about. So what will X be here? Just this X1, X2, right? And approximately equal to this vector. Okay, this vector I'll copy once again. Okay, so this is nothing but whatever we have been seeing so far. AX approximately equal to B. So these A and B now take on very definite meaning. So A holds the features of your data. Okay, they are called the features. In this case, the first column is quiz1 scores. The second column is quiz2 scores. Okay, and X holds the weights. Okay, so what do you mean by weights?
Labels.
A label is B. So whatever this is the label, right? So
Okay.
so what is the weight telling you? It's telling you how important quiz1 is in helping you predict the label. How important is quiz2 in helping you predict the label? So in some term, it could be that quiz1 is a very good predictor of the end term, right? In some terms, it could be that both quiz1 and quiz2 are equally important. Okay, so depending on that, X1 and X2 will change. So that's what you have to find. Okay, the X holds the weights. So X1 gives the importance of quiz1 in predicting the end term score, or in this case, the label. Okay, that's what's called label. B, what is B? So before I go there, I should maybe B holds what are called the true labels. Okay, so comes from your history. Okay, this also comes from your history. That's what the data in this case is history. So x1 likewise x2 gives the importance of q2 in predicting the interim scores, and your goal is to find x such that
So that should be x2.
yeah. So find x such that ax is as close to b as possible, right? So meaning your prediction should be as close to the target as possible. Okay, so you now see the whole apparatus that we discussed before, right? Error will come into play here. So you can define the error in prediction. So now you can define the error in prediction as whatever you predict. Okay, so for a student, it is whatever you predict. Maybe for the first student, let's say, remember that 80 is the correct value. So it is, what is the error? 50x1 plus 70 plus 70x2 minus
80.
whatever in that 80 in this case, right? This whole square. Does everyone get this idea? What is the error? Squared error. Okay, this is the squared error. Now, likewise, you will have, this is for E1, you will have like something similar for E2. Okay, with different values. So I am, in the interest of time, I'm just, so there are 4 students, there will be 4. So E4 is 190 and 190 and
80, I think.
again 80. Okay. Yeah. Okay. So this is, I hope you get the idea. So you have, you therefore have the sum of squared errors, which you have to minimize. Okay. So you want to minimize the error. So you want minimum error. You want as close to be, you want to be as close to the true labels as possible. So therefore, what you do is you minimize sigma ei. Okay, I'm going to use some notation. So ei, maybe I'll call this ei square. So this is the squared error. So let's call this ei square, e4 square. Okay, minimize the squared errors. What is the variable that you are minimizing with respect to?
The x1 and
X1, X2.
Yeah, x1 and x2, right? X1 and x2 are the variables of that. So maybe without summation, this is just okay. So that's what you're doing. Is this setting clear so far?
Yes.
Okay. Now I'm going to slightly move into a different notation to make that might make some of our lives harder, but I have to do that. So remember that I had represented A as A1 transpose. You remember this we did in the first very beginning. Okay, so do you all remember that?
yes.
Okay, so this is what I'm going to make use of. So in this case, what is A1 transpose? 50-70. A2 transpose is 60-60. So you can express the predicted, so you can express the predicted scores as AI transpose. So in this case, you can express the predicted scores as AI transpose X. That's what this is, right? This is the prediction. Remember, it is A1 transpose X. So 50x1 plus 70x2 is the dot product. Is this clear to everyone?
Yes.
Okay. Therefore, the error becomes, or the sum of squared errors, SSE becomes A1 transpose X. Okay, this is the first student. True label for the student or true score, predicted score. So whole square plus dot 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 plus till the mth student. So in this case, there are 4 students. So m will be 4. In general, m students. This is the predicted score minus the true score. Okay. This is the, this is called often, this is called the loss function in machine learning. because it is measuring the loss or the error. Okay, so it's called the loss function. It's also called the error function sometimes. Okay, if you're doing classification, you'll use a different loss function, but for regression, what is called the loss function is the sum of squared errors. So it's called L of x. And now your goal now is, remember, you are trying to approximate, which you have expressed it as a sum of squared errors, and you are trying to minimize the loss function or minimize the error that you make in prediction subject to x. X is the variable of optimization. So we will also study optimization later on in week 8, right, onwards. So we have to know some terminology. So L of x is called the
Loss function.
loss function. That's correct. In the optimization sense, it's also called the objective function. Okay, and this is an example of what is called unconstrained optimization. So there is no constraint. You don't have any constraint. You're allowed to choose whatever x you want. Week 8, week 9, we'll see examples of what are called constrained optimization. Okay, so that's in week 9. But for now, this is unconstrained. Okay, so the immediate solution strategy for unconstrained optimization is, what is it? Does anyone know? If you want to minimize a function, what do?
You do dy by
Differentiate.
Yeah,
Differentiate and equal to 0.
Yeah, so you differentiate. Okay, set derivative to 0. But L of x is what? So actually, L of x is a function of
x1 and x2.
Yeah, of x1 and x2. In general, it's a function of x1. It's a function of x where x is x1 dot 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 x n. It's a function of n variables. So you have to bring in multivariable calculus here. So therefore, what do you compute instead of just the derivative? What do you compute?
Gradient.
Gradient, right? So therefore, you have to compute the gradient and set it to 0. Okay. 0. So gradient, spelling gradient. Okay. So the gradient of L of x is given as the vector of partial derivative. So notice that all that you studied in week 2 and before, they are also now relevant. So this is dou L by dou x1 or dl by dx1, del L by del x1, depending on how you call it. So there are n partial derivatives, and that's the gradient. Okay. So that's what we'll do very quickly. I'll rewrite this so that it becomes easier to find out the partial derivatives. Okay, so all this goes into what are called the normal equations. So we bring that here. So that's a new section. We are trying to solve the equations. Solve the optimization problem, and that will take us to what is called the normal equation. So this is what we have. How do you find the gradient? I'll just give you the intuition. The solution is not too hard. The proof. Okay. So this is let's take one term. Okay, I'll take one term in the sum, AI transpose x minus bi. So if you differentiate this, to take the gradient of this, how will you find the gradient? What is the first rule you will apply?
Chain.
The chain rule, right? So something square. So notice that this is a scalar. Okay, this is a score like 80, 70. This is a predicted score like 75, 55, whatever. So this is a scalar. So you can do 2 times AI transpose x minus bi. Okay, we have done that. Now what is there inside is a vector. Okay, so this is so you are differentiating with respect to vector. Remember, what do you guess the derivative or the gradient of this with respect to x will be?
AI transpose.
Yeah, so it is AI. Okay, so just you are right. So you could represent it as a row or a column vector, but convention is column vector. So you can prove this. It's not very hard. It's actually a very simple thing to prove this. But just intuition wise, what you have to think about it is you can temporarily think of this as scalars. So remember that so if you have something like 2x, remember that AI is constant. Okay, so If you have 2x, then if you take the if you differentiate this with respect to x, you will get 2. Okay, that's what is happening. The x goes away, you are left with AI. So that's all there is to it. Okay, is that clear? Roughly, even if you don't understand it completely, it's fine. So now, if you compute the gradient of x, it's nothing but 2 into, it's just a sum, right? So a1 transpose x minus b1 into a1 plus again 2 into a m. Actually, there are m, right? So there are m rows, m students. So x minus bm into am. So is this clear so far to everyone?
Yes, sir.
Okay, what we do next is there's a slight rearranging that you have to do. So there is, for now, let's forget the 2. So let's say I'm doing half of the gradient. So this 2 goes away. It's cumbersome to have this 2 everywhere. Anyway, I'm going to set it to 0, right? So it doesn't matter if this 2 is there or not. So I'm going to rearrange things. This a1, I'm going to move to the front. I can move it to the front. Remember that this is a scalar. So I can place the scalar wherever I want. So I'm going to do this. Okay. So this is, I hope this is clear to you. I'm just moving the vector to the beginning of the equation. This is the first step. Okay. Second step is I'm going to expand this. So this is a1 transpose x. Okay. Minus a1 b1 plus am transpose x minus am into bm. Okay. So I want you to remember that. Don't forget that ai is a vector. X is also a vector. Okay. And what else do you have to remember? Bm or bi is a scalar. Okay, I hope you are able to. So if you are not able to map it, then think about this as the mark, and this as the weight vector, as we call it, and this is the features, right? One row. So ai is what? One row, or 50, 70, 60. This is ai. This is x. This is b1, b2, b3, b4. Okay, are you all with me so far?
Yes.
Okay, so
Yes.
So what we'll do now is we will take x common. Okay, if you take x common, then what does this become? This becomes a1 transpose plus all the way till am transpose, whole thing into x minus, this is just a1 b1, or I'll call this b1 a1, and you will see why this is useful, and bm am. Okay, so I've just divided it into two parts. All this is what? The gradient, or half the gradient, but as I told you, the half doesn't matter. Okay, now for the final simplification, now for this you have to remember something we studied a long time back. A matrix can be written as, or the product of two matrices can be written as sum of rank 1 matrices. I don't know if you remember this. We did this 4 ways of multiplying a matrix, right? So if you have A, if you write A as whatever, this is what we wrote down as A, right? So this is A. Now remember, this is A, then what is A transpose? What are the columns of A transpose?
A1.
A1. Yeah, exactly. A1 is just A1,
Yeah,
A2,
A2.
so on till AM. Okay. I hope that is clear. We are just swapping the, so see, A1 transpose is a row, means A1 is the corresponding, A1 transpose is the corresponding column. So I'm just going to write it this way. I'm going to move this here, and you will see why that is useful. Okay. Now if you multiply A transpose and A, what happens? You have A transpose here, and you have A here. So you end up with A transpose A becomes A1 transpose plus AM transpose. Okay, this you have to take it.
Yes.
You should remember the fourth way of multiplying two matrices. This is what we discussed. So what you see here is nothing but A transpose A. Okay.
Yes, sir.
Okay. And that is one observation. The second is, if you multiply A transpose B, B, remember, is a vector. So this is what? This is like B1, so on till Bm. Okay, so this becomes, so what is a matrix vector product? It's the linear combination of columns, right? So this is B1 A1 plus so on till Bm Am. Okay, so what you see here is the same thing, B1 A1 plus so on till Bm Am. So now this whole equation, I can just replace this with A transpose A, and I can replace this with A transpose B, right? Are you with me so far? Did this, is it somewhat clear? Okay, so now setting the gradient to 0. So the half you can ignore. So if you set the gradient to 0, you get A transpose AX equal to A transpose B. Okay, so these are called the, okay, so solving this will give you the solution to what is called the least squares problem. Okay, this is a very, very important problem in multiple branches of science and engineering, and of course math. The solution is called the least square solution or least square estimate. So least square solution, least square estimate. So this was pioneered by many scientists. Notable among them was Gauss, Mr. Gauss from the Gaussian distribution, or Gauss, however you want to call him. So in astronomy, right? So trajectories of planets and all that. This was pioneered there, and then it has become a staple problem-solving tool in statistics and, of course, machine learning and several fields, right? So this is the solution. So what have we come to is the following: if a system is inconsistent, then it doesn't have exact solution. So what we can do is we have to settle for approximate solution, and approximation means finding some AX which is as close to B as possible. So if you express that as the sum of squares error, right? If you try to minimize the sum of squares error, then that leads you to what are called these normal equations, and solving the normal equation will give you that best possible solution. Okay, this is the idea. So far, is it clear what has happened, the sequence of steps we have followed?
Yes, sir.
Okay, so there are some points which I'm going to state without proof. The first is, note that this system, this is also a system of linear equation. Okay, that is what you have to understand. So instead of solving, so we can't solve Ax equal to B, therefore we try to approximate, and that has led us to some other system of linear equations where A transpose A is of shape. So if A is of shape M cross N, A transpose A is of shape
N cross.
N cross N. Okay, and X we know is in Rn, and you know that. So what is A transpose B? That's a vector. So this is N cross M, M cross 1. So this is in R N again, right? So remember that A transpose is N cross N, right? So therefore, and B is in Rn. So if you multiply, you will end up with N cross 1. Now, there is a important question that you should ask at this point. What is the question? Does any question arise in your mind? What do you think about this system? What if this system is not consistent? Then whatever you have done so far is moot, right? So there is no point of, you try to solve, you didn't have a solution to Ax equal to B, therefore you came to this, you followed some process, some steps, and you have come to this A transpose Ax equal to A transpose B. But if this doesn't have a solution, then you are once again lost, right? So do you see the problem? Okay, so the question is, what is the guarantee that this A transpose A X equal to A transpose B is consistent? Okay, so that's a question. It's a very interesting question, and once again, you can show that. So one can show that the system is always consistent. That's the beauty of this system.
Because A transpose A is square matrix and invertible, I guess.
Not always. So it is not always, but yeah.
B should belong to
Yeah. So A transpose, but it so happens that you can show that this is consistent, right? And so A transpose A will be invertible when A transpose
B is in the
is invertible provided. Again, this is not very straightforward. A has
Full rank, full column space.
okay. So there is a link between these two. You can actually spend some time and show that A transpose A is invertible provided A has full column rank. But you can rest assured that this is always consistent. So that's what allows us to stop with this equation and not dig in further. Okay, but that's the least square solution. So what do you do here is, where was that? Yeah. So yeah, what you have to do now is, if you are given a system like this, right, in the exam or otherwise, for example, what you have to do is, if you are given something like this, then you should, the steps to follow, right? So step one would be find A transpose A. So that would be A, and then you transpose this, you would find A transpose A, you will get something. And step two would be to find A transpose B. Okay, and I'm just writing down the steps alone. Step three would be whatever you have done so far. So find the augmented matrix, and then do row reduction and solve for X. You will mostly get infinite solutions. So what you have to do is find some particular solution. Okay, so that's the idea. Is this clear so far, what we have done, what we have been discussing?
Oh, there is a small doubt. If A has a full column rank, then wouldn't it mean that null space is 0 and
Yeah.
the equation is
Correct.
consistent?
Yeah, that equation is that's true. So
We are dealing with inconsistent case.
Yeah. So now I'll just make the correction here. So I use the inconsistent part to motivate the whole process of trying to do least squares, but then I'll just make a note. So important remark. If A is full, A has okay. So here's the catch. So if A has full column rank, you still need not have. So it need not mean that your original system is consistent, right? See, when is the original system consistent? When
null space is 0. Yeah.
No, when B is in the column space of A, right? If you go back to the image, the graph that we have been trying to draw. So AX equal to B is consistent if B is in the column space of A.
Yes.
Right? So I could have a system with full column rank. For example, So this is 1 0 0 0, for example. This is one equation, right? So this is AX, so this is x1 x2 x1 x2 only, right? So x1 x2 equal to so 0 0. So this is an example of a system where A has full column rank, right? But it's still inconsistent because B is the idea is B has to be there in the column space of A, which it is not in this case.
Yes, yes.
Right?
Okay.
So consistency has to do with B being in the column space. So you could have full column rank and still have an inconsistent system. So the column rank here, what we are saying is, if A has full column rank, then this system will have a unique solution. That's all we can say. Right? So that is oh sorry, this should not go here. So one can show that system is always consistent and should be a separate point. So when does A transpose A X equal to A transpose B have a unique solution? When null space of A transpose A is 0, which is in fact it's the same as null space of A. We will come back to that later. So when null space of A is 0 or A has full column rank, when that happens, you have a unique solution to the least square system. Okay, so that is, in fact, we can forget this. This is, for now, it might even be confusing. So we can ignore this. What matters now is that this is consistent. So you can always find a solution. Okay, I hope that is clear.
Yes, sir.
Okay, so yeah, any other questions regarding this least squares or linear regression?
So there is this separate question. Can we use linear regression to predict, to estimate time series data also?
I guess you could frame it as a time series problem, but I am not very sure about time series. I have myself not studied time series that much. I have no idea actually. So you'll have to refer to other resources.
Okay.
Okay.
Sir, could you please just again, repeat that thing? Why did we? I mean, how did we arrive this least square problem, sir?
You just
Yeah.
the loss. You first define the loss as the sum of squared errors, and then you want to minimize this, right? So you want to minimize the error in deviation. So it's an optimization problem. So once you want to have an optimization problem, you can, it is unconstrained, you can just take the gradient, set it to 0. So finding the gradient is the tricky part here. So that's what we spent a lot of time on. So this is the gradient finally. And when you set it to 0, you end up with the system of linear equations once again.
Okay. Got it, sir.
I mean, I was thinking, like, if we arranged all the monthly data and found the growth for every month as I mean, assume the growth for every month as x1, x2, xn, and tried to estimate the best values for x1, x2, xn, will it give a very good answer for that? I was trying to think, is it much more accurate, or there are other ways that can be much
There
more
are other ways. So linear regression you could use, I guess, but for time series there are dedicated time series methods. There are even neural networks out there which they're called recurrent neural networks, which work with sequence data. So there are many methods. So I'm not entirely sure what is the best method or what is the state of the art for this. So I I may not be the right person to comment on this. Okay. So
Okay.
we'll very quickly do projections. In fact, we don't have much time, but we'll do projections, and there is actually a link between projections and least squares. But yeah, so what are we doing? We are trying to find a vector Ax that is as close to B as possible. Okay, that's what we are trying to do. Now, what is Ax? What is Ax? It is the
It's actually projection.
well, yeah, but even before, well, it's actually something else.
Linear combination.
Yeah, it is a linear combination of the columns of A. Okay, therefore, what is it? What is Ax? Ax is some vector in the column space of A. Okay, so you can actually rewrite or reframe the whole problem as the following, right? This is an important reframing. So find a vector in the column space of A that is closest to B. Okay, now graphically, what will this look like? I'm going to assume something very simplified here, but it extends to higher dimensional spaces also. Okay, so this is a very simple diagram, but it should be fine. So assume that this is your column space of A. Okay, so remember that column space of, recall that column space is a subspace, okay, of R
Two.
R2 in this case, but in general it is a subspace of
R
M or N.
MM.
M, right? So it's subspace of Rm. So subspaces are what? Lines, planes, things like this, which pass through the origin. So you have to assume that this is the column space of A. Okay, this is the column space of A, and Ax therefore will be some vector on the
Sorry.
column space.
Sorry, one question. If A is an M cross N matrix, then wouldn't column space be a subspace of Rn?
Rm, right? So M
Rn.
plus, no, right? Because each column has M dimensions. M, right? So each vector is M dimension. Therefore, it will be in Rm,
Okay.
right? Okay, so this is Ax. So Ax is something like this. I'm going to call it Ax. So what you want is, what you have is B. So B is sitting somewhere here. So B is also in Rm. So you're actually, in this case, M is equal to 2. So you have some vector B sitting somewhere here, and you have Ax. Ax could be anything in the subspace of anything in the column space of A. So it could go from, it could be anywhere on this line. So what is our goal? Is to find some Ax, some vector Ax that is as close to B as possible. And what is, from geometry, what do you know? Where is that vector going to lie?
Straight line.
It's going to be the perpendicular to. So if you drop a perpendicular
Yes, sir.
from B, so this is B, by the way. So this is B. So if you drop a perpendicular from B, wherever the perpendicular meets the line, okay, that is where your Ax
is closest to.
Okay, so once again, remember in week 2 we studied this B minus Ax, right? If you take the difference between two vectors, what is that vector going to be? Starting from Ax and ending at B. Do you remember
Yes.
that we studied this?
Yes, sir.
Okay, so this is actually B minus Ax. So if I draw this kind of arrow, and make these perhaps a bit lighter, we understand where the arrow is pointing. Sorry, I'm taking time, but if you want to do it somewhat properly, you need to. Yeah, so this is b minus ax. And what is ax? Ax itself is this vector. So I hope you're able to see that. Okay, ax itself is this vector. So using the notation of perpendicularity, b is perpendicular to,
Ax.
sorry, not b. What is perpendicular? Ax is perpendicular to b minus ax, right? Is this fine with everyone? These two vectors are perpendicular. Clear, right, so far?
Yeah.
Okay, if two vectors are perpendicular, then there, what is zero?
Dot product.
Dot product. So ax transpose b minus ax is 0. Okay, ax transpose b minus ax is 0, which is the same as saying, so if you take ab transpose, it's b transpose a transpose. So it's actually x transpose a transpose, okay, into b minus ax is 0, which is the same as saying that x transpose a transpose. Okay, let me start over again. It's actually easier to do it as b minus ax is 0, right? Symmetry, if you recall, so it's a symmetric operation. So I can do this. This is easier. Okay, that's why I'm doing. Both are the same. So this is b transpose minus ax transpose. Okay, that is what this is, into ax equal to 0. So this is b transpose ax minus x transpose a transpose ax. Is this clear so far? I have just expanded. So b transpose ax. Is this clear to everyone?
Yes, sir.
Okay. There seems to be some mistake somewhere. Wait one second.
B trans.
Okay. So scratch the whole thing. What I've written is not wrong, but this is not what we need. Okay. So yeah. So sorry. This is I need to b minus ax is perpendicular to x. That is correct. But then so observe that b minus ax is perpendicular to the column space of A. Okay, that is what we need. So remember that this line, okay, b minus ax is perpendicular to the entire line. Okay, is this fine? So if b minus ax is perpendicular to the column space of A, then this means that, what does this mean? B minus ax is perpendicular to every
Point on
ax on ax.
the X on.
every dash of A.
When you actually vectors, that's column space of A actually.
Okay, so it is perpendicular to every vector in the column space of A, but you can simplify it to something. How can you simplify this?
Again, the null space of again.
See, this is b minus ax. Okay, it is perpendicular to this line. So this line is the column space of A. I'm saying. So I'm trying to.
Is it perpendicular to every column?
Yeah, every column of A, right? So if it's perpendicular to every column of A, then naturally it's going to be perpendicular to all vectors in the span of the columns of A, right? The first requirement is every column should be perpendicular to b minus ax. Then only we can say that b minus ax is perpendicular to the column space of A. Is this clear?
Yes.
Okay, so this once again, remember that the columns of A are the rows of what?
A transpose.
A transpose, right? The columns of A are the rows of A transpose. So if b minus ax is perpendicular to the columns of A, then it's perpendicular to the rows of A transpose. So A transpose into b minus ax. Okay, remember this is just row transpose b minus ax, second row transpose, or rather this is first row dot product with b minus ax, second row dot product with b minus ax, so on and so forth. So this entire thing is equal to the 0. What is this 0? Is it a scalar or a vector?
Vector.
It's a vector, right? So now if you expand this, you get A transpose B equal to A transpose AX. In fact, if you rearrange this, what you get is A transpose AX equal to A transpose B. Okay, this is nothing but the equation that we obtained here. Okay. So geometrically, what you are doing is, so geometrically, the least squares system or least square solution is trying to find the projection. Okay, this is
Best projection.
the orthogonal projection of B onto something. What is this
Column
something?
space. Okay.
Column space. Okay, what are you trying to do? So this is the column space of A. You are trying to find some projection onto the, so not some, the projection of B onto the column space of A. Okay, that's what you're trying to do. So, and if you solve that, the resulting projection is what?
It's
The best projection.
It is actually A times that X, right? Whatever X comes out, AX is actually the projection of, as we saw here, right? So it's already 6. So I'll close with projection matrices. Unfortunately, we don't know if we'll have time, but let's quickly do one example of a projection, right? So projection where A is just a vector as done in the lectures, so that we close that. So this is, let's say this is B is equal to 1, 3. Okay, it doesn't matter what exactly this is. This is okay. So this is going to be what? One group. This I'm going to call this the vector that goes through this line. Let's call that A. Okay, and what is A going to be? Let's say 2,1. Okay, something, some. So now, what is the projection of B onto A going to be? The foot of this perpendicular, right? Do you all agree that that's going to be the, let's call that projection. So how can you represent this yellow vector here? Let's call that C. How do you represent this yellow vector in terms of A, B?
It is A times of C, can we say?
Yeah, it is some A times what? Alpha. So let's say it's alpha times something. What is that something?
It is A times alpha actually.
Yeah, A times alpha, right? So this is alpha times 2, 1. Okay, or A times alpha times A. It's clear to everyone? We don't know what alpha is, but that's the idea. Okay, so now B, so something is perpendicular to something. So can you tell me what is from the diagram that you see here? What is perpendicular to what?
C is perpendicular to B.
B is perpendicular on C.
B, see, B is this vector, right? So you should actually, B is this vector. So, okay, that is B. This is the C. This is C. And A is this one. Okay. These are the 3 vectors. So now can you tell me, based on what you observe, what is perpendicular to what? Let me just call this C. Okay. We don't know what C is. Yeah. So something is perpendicular to something. Whatever we have just studied, right? So
C is perpendicular to B.
C is perpendicular to
B.
C and B are different vectors, right? So this is C, this is B. There is some acute angle here. So
B minus C is perpendicular to C.
sorry, can you repeat that?
B minus C is perpendicular perpendicular to C.
Yeah.
Yeah, B minus C, right? So this is what is. So remember that this is B minus C. Okay, so please remember that B minus C is what? You start from the foot, you start from C and go to B. So see, C plus B minus C should give you B by the triangle rule of addition. So it is B minus C which is perpendicular to C or to A. So you can put it either way. So let's say it's perpendicular. I'll just use A here. So therefore A transpose B minus C is 0, correct? And you can write this as A transpose B minus some alpha times A is 0. Okay. And if you expand this, alpha is equal to the ratio of two things. What is it? A transpose B by
A transpose.
A transpose A, right? Okay, so this is alpha. Now, this is often called the scalar projection. So this is the scalar value. The projection of A of B, okay, onto the line given by the vector A, okay, is nothing but C. Okay, C is that value. C is alpha times A. So this is nothing but A transpose B by A transpose A into A. Okay, remember that this is a vector. So the vector is a vector because you are multiplying a scalar by A. So A is that vector here, right? So it's a vector and this is what you have. So A transpose B. In this case, if you want to actually compute it, what B is 1, 3. So B is 1, 3 and A is what? 2, 1. So this would be, the projection would be A transpose B, which is 2 plus 3, 5 by A transpose A, which is norm A square, right? Is also the same as A transpose B by norm A square. You can also express it that way. Okay, in fact, you can also express this as, there are so many ways to express this. Each one has its own utility. So this is, can bring A by norm A inside, okay, transpose that with B. And then you can multiply that with A by, okay, this is also a very popular way of writing it. But anyway, so this is there, right? So this is what? 5 by, oh, this is 5 by 5, is it?
Yeah.
Oh, very sad. Yeah. And the diagram is totally incorrect. Then, so the projection of, so you end up with, the diagram is incorrect. So maybe let us draw the vectors here. So you have the vectors, not, what are they? 3, 1. You remember what they were? 1, 2 or 2, 1? 2, 1 and 1, 3, is it? 2, 1 and
Yes.
1, 3. Yeah. So it so happens that they are well placed. Okay. So if you now draw, so what you have to now draw is a vector starting from 1, 2, or rather 2, 1,
Ending at
and ending at
1, 3.
So you see that this is perpendicular. Okay, that's what we had. Anyway, we were lucky to have alpha equal to 1 here, but so that's the projection. So the projection of projection of B on A in this case is just A itself, but it need not always be the case. Okay, so in general, the projection of a vector B onto a vector A is given by, finally, so B transpose A by A transpose A. Okay, so if the vector A happens to have unit norm, meaning what is unit norm? Norm A square is 1, right? So norm A is 1, just like A transpose A equal to 1. So if this happens, then the projection of A of B onto A
Is
can
it
be expressed as what? Just B transpose A. That's a great advantage of
yeah,
unit
denominator
properties,
should be
right? So notationally, it's very simple. B transpose A, it's just the dot product times A. So now maybe I will just, since we have already run out of time, I'll quickly represent this. So this is, if you rearrange things, remember that this can be rewritten as, you just move the so A transpose B transpose A can also be written as A transpose B, and A transpose A remains here. Okay, so this can be written as 1 by A transpose A into A transpose. Okay, the whole thing into B, right? So you can you can call this P as, okay, as the projection matrix. So P is of shape. What is the shape of P? If A is of shape n cross n, so or A belongs to Rn, then P is of shape
n cross 1.
n cross n, right? So it's a projection matrix. So P projects vectors in Rn onto the line which passes through vector A. Okay, so is this clear? P equal to 8, what we mean by this? Okay, so there is actually something more to say of projection matrices for which we don't have enough time. This is actually only a small part of, in general, projection matrices can be found for any matrix A. If you want to project to the column space of A, there is a much richer theory for projection matrices. I'll just leave a couple of points here, so you can, in general, you can find a projection matrix for any subspace of Rn. Okay, and projection matrices satisfy the following properties, right? So two very important properties. First is that P square equal to P, right? If you square the projection matrix, you'll get back P itself. It's a nice geometric interpretation for this, but we don't have time for that. Second is that projection matrices are symmetric. Okay, so P transpose equal to P. Any projection matrix that you can think of has to satisfy these two properties. In fact, it goes both ways. So some P is a projection matrix if and only if P square equal to P and P is symmetric. Okay, so I don't have time to discuss this today, but maybe we can see this for P here, right? For a projection matrix that projects onto a line. So what is P square? A transpose. Yeah, once again A transpose. Okay. And in the denominator, you will get 1 by A transpose A whole square. Okay, and one of these will become A transpose A, that will go out. So you'll end up with, once again,
A transpose.
A transpose A, which is again P. Okay, so this is like,
So where does B goes from the
B goes from this because this is so yeah, this is the projection of B onto the line A that is given by this. But then if B keeps changing, right? So what is the matrix that is responsible for the projection? That is P. So
Okay.
this thing becomes P. Okay. So therefore, I should say that therefore the projection of B onto A is given by PB. Right? So if you multiply, you should think of this as a linear transformation or a linear map which converts one vector to the other. The conversion here is that A becomes P times A. B becomes P times B. So B becomes P times B, where PB is the projection of B onto A. So you can also verify that PB. So remember that if you subtract the projection from B, you should get something perpendicular to A, right? So it has to be true that P minus PB is perpendicular to A, right? So you can verify that. So what is PB? It's just A transpose B by A transpose A. Okay, that is PB, and B minus PB will be this. So is this perpendicular to A? So for that, what should you do? You should do A transpose this. Okay, so if you do A transpose this, you get A transpose B minus A transpose A in the numerator. Okay, there is an A transpose A in the denominator. And then you anyway have an A transpose B. So that is 0.
We can look it from the take it from the figure also.
Yeah, figure also. Yeah. Okay, so that is all we have time for. Maybe we should discuss projection matrices next week in more detail when we have. Yeah, so any questions? Okay, so can we stop then and meet again next week?
Yes.
Okay. All right then. Yeah. So we'll meet again soon.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.